Okay, so hi everyone. Thank you for being in the presentation here. So this fall, this summer semester, what I did was I actually was virtual here at my home and was working remotely. And what I did research on is evolution of turbulence in the heliosphere using the Helios 2 measurements. So let's start off. Okay, so let's discuss about the solar wind first. So solar winds are formed when neutral hydrogen particles are ionized by solar wind protons. Um, so it's a stream plasma and particles from the surface of the sun. So it speeds up between 250 and 750 kilometers per second. And there are two types of solar wind. Those are fast and slow wind. So we categorize it in terms of how fast the speed is. And the solar wind is very harmful for human and it can cause radiation poisoning to humans. And fortunately, we have Earth's magnetic field, which deflects all the solar wind, and that's how we are alive. So let's get into the next slide and let's talk about turbulence. So how the turbulence is created is it's because of the solar wind. Is whenever the fast and the slow wind it interacts in between, there is a turbulence in between those solar winds. So as you can see here in the picture, so the fast wind is blown from the top of the solar corona and sun corona, and the slow wind is blown from the middle of the sun corona. So in between there is a turbulence, which is what we are going to discuss about today. So basically turbulence is a irregular flow of motion and it's driven by the fluctuation and it's caused due to fast and slow wind, as I discussed, present throughout the solar wind from the solar corona to all the way to the heliopause. And heliopause is a space way outside of the solar system. So this picture is basically solar wind being deflected by Earth's magnetic field. Here you can see the blue picture, blue lines here. It depicts the magnetic field, and solar wind is all deflected by the magnetic field here. So let's talk about how I got the data from. So I actually imported the data set from NASA's website, and Helios 2 was a spacecraft which was a cooperative project between US government and Germany. It actually observed solar environment, which is basically the solar winds, and it actually grabbed data related to turbulence. And it flew at a distance of 0.29 astronomical unit, which is way closer than Helios 1. So I actually got the data of velocity, magnetic field, and RTN components, which we are going to discuss about it later on. And so that's how I calculated the turbulence and the fluctuation of all those parameters. So goal of my project was to observe the turbulence in the magnetic field, SSR energy, velocity, and calculate correlation length caused due to the solar winds. So turbulence is actually a fluctuation, and in mathematically, it's variance. So I was assigned to calculate the variance and fluctuation in magnetic field and all those LSSR energy, how it is behaving in the fast, like in terms of fast wind and the slow wind, etc. And also to normalize the transport modal equations and plot the data points to compare with the observed data. So the data was taken from the Helios 2 spacecraft as mentioned. So let's talk about RTN components. So when a curve is defined in terms of the in function of time, T component is actually a unique tangent vector to the curve, which is a tangential component, and a normal component N is a normal vector to the curve defined by R in function of time. So I have all this data, RTN components, and which also helped me calculate the magnetic field, magnitude of the magnetic field in total, and also a magnitude of velocity in total. So this is how the graph looks like when I plotted magnetic field versus distance in astronomical unit. You can see the N component, it stretches all the way to the bottom, while B component is actually calculated using R, T, and N component, which usually is in between the range of 10 to the power 1 and 10 to the power minus 1. So my initial half of this semester was basically cleaning the bad data that was present in the data imported using the Helios 2 data, and I actually used pandas to clean the bad data. And I plotted the data points against the distance between 0.29 to 0.98 astronomical unit using NumPy, which is also a framework of Python. And I calculated LSSR energy using RTN components of magnetic field and velocity. And later on, I also calculated normalized residual energy and residual energy. So it's basically came from the parameters that were actually recorded by the Helios 2. And I also calculated the variance for all the parameters mentioned as a, mentioned, and the variance means the fluctuation here. So the equation involved, as I said, I calculated LSSR energy using RTN and components of magnetic field and the velocity. So you can see here LSSR energy, it's calculated the positive LSSR energy, which means the forward propagating solar wind, and LSSR energy G minus means the backward propagating solar wind. So I calculated the LSSR energy using this formula, and later on plotted it against the distance. So the basic formula of the variance is basically this, and later on I also calculated normalized residual energy and also residual energy. So what are the steps taken? So to actually code it through and have a plotted graph, I had to clean the bad data as mentioned, and later on I need to tweak some programming concept in it, and also took 8 hours of interval and made a block for each interval. Let's say like for 8 hours of the data, there was one block, and for the next 8 hours, that was another block. And I actually calculated the blocks from the time frame of January to all the way extending until April. So it was probably like 260 blocks. And after that, I calculated LSSR energy, magnetic field, velocity for each of the blocks. Then I exported the data from this research paper of my mentor, Al Adhikari et al. To 2015 to compare my observation to the papers. So the next step and next assignment for me was to actually solve the transport equations, which was a little bit tough, but I was assigned to normalize the equations, and later on output the data points and plot it against the observed plotting. And we consider lambda minus, which is a correlation length, to be a lambda as well, and positive correlation length to be a lambda, and lambda d to be a 2 lambda. And also normalized the equation using all these methods here, which is how it made me easier to solve the equations. And after I plotted it, as you can see, the graph here, this is all the fluctuations, which means the turbulence in this heliosphere, which is in between sun and earth. So if we observe this data, if we observe the fluctuation in the magnetic field, we can see that it's decreasing whenever there is less turbulence, or whenever the distance is more. So there is a less turbulence. So that's what my observation was from all the data. And the green points are actually from the transfer model equation, and blue points are my data, what I imported from NASA's website and plotted it against. And this is a normalized residual energy versus distance. You can see it's also decreasing. And this is a fluctuation in velocity versus distance, and which also depicts that it gradually decreases, the fluctuation decreases with increase in the distance, meaning whenever the distance increases, then there is a less turbulence. So since there is the magnitude of the solar wind, it's not that very much, and the fluctuation decreases. And here is the LSSR energy here. And the LSSR energy, we can see that it's decreasing. It's not the positive energy. which is the forward propagating energy, is decreasing, but it's in the range of 10 to the power 2 and 10 to the power 4. And that's how it will be. So my observation and the data points which was taken out of the transfer model equation, it actually resonated, which means the observation was quite successful. And positive, forward propagating and backward propagating energy was decreasing, both of them as well. So the conclusion was basically when there is no source of turbulence, the fluctuating magnetic energy decreases rapidly. With the stream source or turbulence, the fluctuating magnetic energy decreases less rapidly there. So I would like to thank Dr. Laxman Adhikari for the mentorship and help throughout the internship period. My sincere gratitude to NASA Science Foundation, EPS COR, CPU 2L, and ALPIP for funding the research. I'd like to thank Dana Walker for helping me throughout the process. Thank you very much, Dana. And any questions? Thank you.
Hi, my name is Flasny, and thank you for watching this video. Make sure to follow us on our social media at CPE2AL on Facebook, LinkedIn, and Instagram. Bye!